All right, in this video, we're going to be working linear algebra homework 6.2. We're going to be computing a bunch of determinants. So we're going to compute the determinant of A using cofactor expansion. Okay, for the first set of how many? 3, we're using the long way, cofactor expansion. So we're going to say, all right, I can pick any of those 3 rows or columns to kind of start off with. So I'm going to choose the one that has the 0 in it. I'm going to do the 1, 0, -1. So I'm going to have 1 of something. What's going on here? Just want to use the pen. Let's see, is that? Yeah, there we go. All right, so 1 of something minus 0 of something else plus 1 of a third thing. Okay. Now, when I do that first one, I'm going to remove the first row and the first column and take the determinant of what's left. So 3 minus 2. Then with the 0, it doesn't matter because 0 times anything is going to be 0. Plus -1, I don't know why that would be a minus. Let's get that one out there. -1 times, get rid of that row and that column, take the other determinant, that's 4 minus 3. Yeah, you can see my cursor. So 4 minus 3, okay, that's going to be equal to 1 minus 1, and that's going to equal 0. Yes, definitely. If you add row 1 to row 3, you are going to get row 2, so that would mean A is a singular matrix, and we have known in this class that singular matrices have 0 determinant. All right, so I'm going to get rid of all those. That determinant was 0, so for 1b, I might label my work a little better over here moving forward. All right, so I'm going to use that first row. Clearly, this determinant is going to equal 2 times the determinant of 3, 1, 2, and 4. Okay, so that's going to be 2 times 12 minus 2, and that's feeling like 20. And then C is a 4 by 4 matrix. And, okay, so I'm going to, I'm obviously choosing that first column to work with, so the determinant of A is going to be 1 times the determinant of 3, 0, 0, 4, 1, 2, 3, 1, 4. Okay, and then I'm going to say, all right, hold on. Oh yeah, okay. In this subdeterminant, I'm going to clearly be choosing the top row, which is going to be, okay, so minus 0 times, plus 0 of some other subdeterminant minus 0 of the last one, because it's 4 by 4, it's going to be, 4 subdeterminants. Okay, so this is equal to 3 times the 1 times 4 minus 2 times 1. Okay, so 3 times 2 is going to equal 6. Okay, again, there was going to be a kind of a minus 0 of something plus 0 of something else, but I'm making use of those good rows with a bunch of zeros. And that was 1C. Let's see, I am going to need a new page, but I don't need it yet. All right. Oh, no, that's not how that's going to go. Well, for number 2, it looks like we've got some triangular matrices. And so for a triangular matrix like this, we can just multiply down the main diagonal to get the determinant. Hopefully that's something I showed you about in class. I think, yeah, and I think I definitely showed you that. Because it's related to the row reduction trick. Okay, so the determinant of this matrix is going to equal 2 times 4 times 1 times 3. So that's going to be 24, and I think I actually don't need quite that level of zoom. Okay. So I guess that was 2a. Okay, and then this one is also triangular, but not exactly. Okay, so it's kind of like backwards. It's not the type of matrix we are very familiar with at all. I'm thinking if okay. I don't know, but even still. Okay. My conjecture is that we can just take I'm not exactly seeing why, but it's going to be 3 times 2 times 3 times 2. So it's going to be 36. Okay, but I'm not convinced. I just feel like there's something off here. I don't love it, but what I know is that adding multiples of one row to another row does not change the determinant. So I know that the determinant of this matrix is going to equal the determinant of, that'll be fine, 0, 0, 0, I'll leave that 2 there, but I am going to be able to clear out the rest of the column without changing the determinant. So 3, 4, 1. Okay. And that's a determinant. But this is going to also be the same determinant if I subtract a third of row 2 from both row 3 and row 4, as in like turn those into 0. It's still got the same determinant. And then, apply the same process here, still got the same determinant. Okay, and you might be thinking, okay, that's still not a diagonal matrix. It's not. Okay, but it's only off from being it by some row swaps. I think what I would do is maybe swap rows 1 and 4 and then 2 and 3. An even number of row swaps is going to get the job done. Okay, so that has the same determinant as the diagonal one, and that's 2, 3, 2, 3, which is going to be 36. So yeah, I feel better about that now. I think I just needed to run through that and convince myself. I think I knew that at one point sometime in the past, but had not been knowing that recently. All right, so 3a. Okay, determinant using row reduction. Okay, so the determinant of B is going to equal the determinant. I'm going to start with a row operation, and I'm going to try to just get as many in as I can by just subtracting multiples of one row from another row, so I don't change the determinant, and try to avoid using like row swaps or just like multiplying a row by a non-zero constant, if at all possible. So I'm going to subtract 2 copies of row 1 from row 2, and I'm going to get 1, 0, 0, 1, negative 1, 0, right? Yeah, so I'm gonna, because I subtracted 2 negative 1s. Okay, and then I've got still this 0, negative 1, 2. Okay, now I'm gonna do another one. I'm gonna add row 2 onto row 3. 1, 0, 0, 0, 2, and now I've got a triangular matrix, and I can multiply down the main diagonal. That's going to be 1 times 1 times 2, and that will be a determinant of 2. Okay, so that's a pretty good example of an easy one that we're going to compute using row reduction. Right. For the next one, okay, good, we got 3. Let's say the determinant of this matrix is going to be the same as the determinant of, and I'm going to make some row operations. I'm going to add row 1 to row 2. I'm not going to do anything to row 3. I'm going to also subtract row 1 from row 4. Okay, so I'll deal with row 2 first. I'm adding down. So 3 minus 1 is 2, 5 plus 1 is 6, 7, and 1 is 8. Okay, then I'm subtracting from row 4, 0, 0. Okay, 2 minus 1 is 1. 1 minus 1 is 0. Okay, that's interesting. Okay, so this, I can tell this matrix, this problem, it's like really going to be encouraging me to do a row swap. Okay, I've done nothing to row 1, so I should probably copy that in also. Okay, now for row 3, 2, 6, and 9. Okay, yeah, I'm going to just subtract row 2 from row 3 and have row 3 be 0, 0, 0, 1. In fact, I can just probably do that right now. And so, okay, if I do a row swap, that would make the determinant negative, so it would be the negative of the determinant of 1, negative 1, 1, 1, 0, 2, 6, 8, 0, 0, 1, 0, 0, 0, 0, 1. This is triangular. I could take the determinant by multiplying down the diagonal. That determinant would be 2. Our determinant is negative 2. Okay, so I'm going to add row 1 to row 2. I'm going to add 3 copies of row 1 to row 2. 0, 5, -6, 5. Okay, now I know that because I have 2 identical rows, I've got a singular matrix and the determinant's going to be 0. I don't need to go any farther. And I'm not going to. I'm just going to go 4, 4, 6, -1. Whoops, I don't know what's going on there. And I'm going to say, okay, well, here we go. I know that's going to have determinant 0. I think that's self-evident. In my class, it would definitely be okay to just say, okay, that determinant 0. I can just look, 2 rows are the same. If I row reduce it all the way, it will have a row of all zeros. Okay, and no matter what, you know, it's gonna that means the determinant would be proportional to 0, which means 0. All right. That was kind of a disappointment. I hope that wouldn't happen, but it'll be all right. All right. So let P be this matrix here. Suppose Q is a 3 by 3. Oh, well, I was like, oh, I don't want to take that determinant using row reduction, but I don't need to. Just like, you know, take it with cofactor. Think about the first row, 1, 0, 0. So the determinant is going to be 1 times 30 minus 28. So another determinant of 2 minus 0 is something plus 0 is something else. So it's going to be determinant 2. All right, so I know for a fact that determinant P equals 2. Q is a 3 by 3 matrix where determinant Q equals 3. Okay, suppose... All right, looks like we're going to be using our determinant property. So determinant of PQ, that's going to be the determinant of P multiplied by the determinant of Q, and that's going to be 6. Let me just upgrade this to all of the number 4s. The determinant of P multiplied by Q transpose. We know that the determinant of Q is equal to the determinant of Q transpose, so PQ transpose is the determinant of P multiplied by the determinant of Q transpose, which is going to be 2 times the determinant of Q, because those are equal, and that's going to be also 6. All right, then determinant of 2PQ. So that's the determinant of 2p multiplied by the determinant of q. Okay, and that's not just going to be 2 times 6, okay, because in order to multiply p by 2, we would have to multiply all 3 rows of p by 2, and so we would be multiplying the determinant by 2 3 times, so that would be multiplying by 8. Okay, so that's going to equal 2 to the third, because p is a 3 by 3 matrix, multiplied by the determinant of P, multiplied by the determinant of Q. And so that's going to be 8 times 2 times 3, and that would be 48. And then QR. What is QR? Or what is R? Oh, R is a singular 3 by 3 matrix. I didn't catch that. Okay, so I've also got, if it's singular, its determinant is 0. Okay, so the determinant of QR is also going to be 0 because that's the determinant of Q multiplied by the determinant of R. Okay. So, oh, oops, I missed that one in the middle there. Okay, and then we've got this Q inverse, P inverse. So, okay, so that's the determinant of P inverse multiplied by the determinant of Q inverse. The determinant of the inverse is the reciprocal of the original determinant, so that's going to be 1 over the determinant of P plus 1 over the determinant of Q. And so that's going to be a half plus a third. That's going to be 5 over 6. Okay, that was an interesting one. Okay, now we've got here, find all ordered pairs that make the matrix singular. Okay, so singular has a 0 determinant. Determinant's kind of the theme here. So what we're going to do is we're just going to take a determinant. I think I'm going to take the determinant of this one using cofactor expansion along the first row. So the determinant of A is going to equal, x times something minus y times something plus 1 times something else. So it'll be x times 3 plus 1 plus minus y times 2 minus 0 plus 1 times negative 2 minus 0. Okay, so 4x minus 2y minus 2. Okay, so if it's singular, we need the determinant to equal 0, so that's 4x equal, I guess I could solve for it if I wanted, but 2y minus 2 equaling 0, that would be y equals, we would have 4x minus 2, so that'll be 2x minus 1 if I solved for y, and then if we wanted to, we could sketch the set of all ordered pairs that make that happen. Okay, if it's 2x minus 1, we need the y-axis to come down there, and then we're going to have for ourselves a graph. I guess that's believable. Okay, that's all the ordered pairs for 5a. Okay, and then for 5b, we're going to do the same thing. I'm going to do cofactor expansion along the first column, though, because I see that 0. Okay, so the determinant of A is going to equal x times something minus 2 times something else plus 0 of a third thing. So x times y plus 1. Ooh, interesting. Okay, minus 2 times, wait, I don't know about, okay, no, that was legitimate. The 2, I'm removing the first column and the middle row. I'm doing y minus negative 1. Is that? Okay, because the first and second rows are equivalent when I was covering stuff. Okay, it's the same. Yeah, it seemed weird to get the same thing on two different subdeterminants. Okay, 0, get rid of that row, get rid of that column, so that would be 1 minus 1. Oh, well, it doesn't even matter because it was going to be 0 anyway, but I do have 0 times 0. So, okay, it's x times y plus 1 minus 2 times y plus 1. So I'm going to factor that. I can, if I'm interested in where this equals 0, I can factor out the y plus 1 and be left with x minus 2. Oh, and this is an interesting set of points. I think we may have run into, I don't know if I'd call it a graph, but like a situation like this. But use the zero product property, these two things will multiply together to equal 0 anytime y equals negative 1 or when x equals 2. So it's going to be the union of two lines. All right, so y equals negative 1 down there. That is a horizontal line. And then I could draw x equals 2 over there. So anywhere on the red or blue line, okay, these are ordered pairs that make the determinant equal to 0. Okay, and that's all for this problem set, right? Yep, so that's all for this video. Thanks for watching.